Hey guys, today we're going to be talking about some of the specifics of what we've been looking at in class the last couple days, specifically uniform circular motion, or as we will often refer to it, just UCM. Now, up until this point, all of our motion that we've been looking at has been linear, so in a straight line, but even though we are talking about objects moving in circular paths, we can also consider what we do call the linear distance of that object moving in the circle, and that distance is the distance around the circle. So the circumference of the circle. When an object is traveling in that circular path, the distance it travels is the circumference. And as we hopefully remember from math, the relationship between radius and circumference is a proportional one, where the circumference is equal to 2 pi r. So if we take that into account and we look back at our equation for uniform speed, and remember that in this case we are talking about speed, not velocity, because as we've mentioned in class, the velocity is constantly changing. So our equation for speed is d over t, or distance over time. And recall that distance is also a scalar quantity, just like speed is, so the direction doesn't matter. So even though the direction of our circle is constantly changing as we move around it, that's okay for distance. And even though as you move around the circle, you keep coming back to where you started, your total displacement might be 0. Because distance is scalar, that's okay. It's simply the distance around the circle. So as we just said, in the case of a circle, the distance we're going to use is 2 pi r. The time that it takes for an object to move around in a circle, it's still a time. We give it a specific name when we're talking about cycles, whether it's uniform circular motion, simple harmonic motion, wave motion, etc. We call it the period. In this case, it is the period of revolution, how long it takes for the object to go around one complete time. And we distinguish time, just in random time, with period by using a capital T. So when we see that capital T, we know we're talking about the time for something that occurs cyclically and how long it takes for one cycle of that particular system. So then if we put that into our previous distance over time equation, we get our speed of an object in uniform circular motion is equal to 2 pi times the radius divided by t, which is the period. So we can see that there is a proportional relationship between the speed and the radius, and there is an inversely proportional relationship between the speed and the time. Okay? Now, just as we mentioned, the period of rotation is the time for one full revolution. And we can get that. We might have an object that travels an arc that looks like that. If that's half a circle and it takes 0.5 seconds, yes, that's half a circle, then obviously the time for a full circle would be 1 second. So we may not always be given the time for one cycle, but we should be able to determine what that period is based on the other information given. The other piece of that period idea, though, is what we call the frequency. So period is the time for one cycle. The frequency is the number of cycles in 1 second. And these two values are inverse of each other. So the period is 1 over the frequency is 1 over the period. So let's say we have a ball on a string that travels around in a circular path, and the time it takes is 4 seconds for 1 cycle. So then our frequency would be 1 over 4 seconds. So that's 0.25 cycles per second, which this units of cycles per second is hertz, which we symbolize with a capital H, lowercase z. And we're going to see both these terms, period and frequency, throughout the next couple of units. So, as we talked about in class, the direction piece then of our velocity is this line that's tangent to the circle. And so at any point, we've got 2 shown here, but we could also look at it here. The length of this vector, so the magnitude of our velocity, is going to be the same at any point along the circle. The thing that's going to be different is going to be the direction. And so because that direction is changing constantly, that tells us the object is accelerating despite the uniform speed. And this is how we just mentioned, speed and direction. So moving in a circle, object still undergoes acceleration because its direction is changing. So that piece is really important. And anytime we have this, anything that's going towards the center of a circle, that center seeking, that's where that term centripetal comes from. And so this is what we call centripetal acceleration. And often in equations, you'll see that with an a subscript c. So the lowercase a for the acceleration, subscript c to specify that it is a centripetal acceleration. And just like with any net or with any acceleration, if there's acceleration, there must be a net force. And we remember from previously in the year, the acceleration is proportional to the net force. This is true always. And it's also in the same direction. Now, if we look a little bit more closely at our velocity vectors, we can see how we can determine, or we can kind of work through our derivation for finding the acceleration. Now, you don't necessarily have to know how we get to our final equation, which is that the acceleration, the centripetal acceleration, is equal to v squared over r. But I think it's interesting and worth taking a minute to look at. So if we have 2 different points, we have a velocity at 2 different times. So we have v1 that's right here, and then some short time later we have v2 here. If the time is short enough, and so we look at a really tiny fraction of time, then in that time, the object is going to move through some angle, and we can actually approximate this arc length here with this side S here. So over a very small period of time, those 2 distances, the arc length and the length of that triangle, are close enough that we can use one interchangeably with the other. Now, if we put our velocity vectors tail to tail, here's v1, here's v2, the difference or the change in those two velocities is represented by this arrow here. Actually, let's keep it red. This arrow red, which we'll call delta V. So, with our similar triangles, because this angle and this angle then are the same, we come up with this equality here, where side S over R is equal to delta V over V. Now remember that both of our R's here are going to be the same because that's the radius. Both of our V's here are going to be the same because that's the speed. Okay? So then, if we, as we said, approximate that arc with the chord S, then we can say that that S has a length that's equal to the velocity times the time. So this is basically just coming back to our velocity equation, where we say that velocity is equal to distance over time. In this case, our distance is the chord S, and so we have S is equal to velocity times time. We're going to plug that in here, and what we're going to see is that we can, let's get a different color here, let's go with blue. We have V delta T over R equals delta V over V. Recall that our definition of acceleration is delta V over delta T, so I'm going to divide both sides by delta T, which is going to cancel them out over here. So I get V over R equals delta V over V delta T. I'm going to multiply both sides by V. So what I end up with is V squared over R equals delta V over delta T. This right here is the definition of acceleration. So our acceleration then is equal to V squared over R. And this is, of course, just for centripetal acceleration. So the speed squared divided by the radius. Now, that's really the hard part of this, because then, once we have our acceleration, our net force equation doesn't change just because we're talking about circles. Our net force is still equal to the mass times the acceleration. In this case, our net force is the centripetal force, so we're going to write that as F sub c, and our acceleration is the centripetal acceleration, so it just becomes Fc equals m times acceleration, or a sub c. As we just saw, the acceleration in the centripetal direction is v squared over r, so we can plug that in to our AC here, and we get an equation for centripetal force where it is the mass times the velocity squared divided by the radius. So this is also sometimes written as Fc equals m v squared over r. Of course, these two are mathematically equivalent. Now, as we start working through this, it's really important to understand that centripetal force isn't one of our basic forces of nature. It's not like our normal force. It's not like a gravitational force. It's not a frictional force. The centripetal force can be any of those forces, or any force can be a centripetal force. It's whatever the net force is that's directed towards the fixed center. So, in our tennis ball on a string, moving around in a circle, the centripetal force, or excuse me, the tension force is the net force, and so the tension force is the centripetal force. For a car going around a curve, Okay, the tires are exerting a frictional force on the road. The road is exerting a frictional force on the tires. And so in the case of our car, the frictional force is the net force in terms of the curve, and so the frictional force is the centripetal force for a car going around a curve. We can even take it up to the level of our planets orbiting around the sun, and in the case of our planets orbiting, or in any type of orbit, the force that's keeping those planets in orbit is a gravitational force. So in that case, the gravitational force is the centripetal force. And we're going to actually come back to that in a week or so and talk more about the force of gravity. Okay, so as we said in our awesome diagram here of our girl spinning the tin can, the force that's keeping the tin can from moving around or moving out, having its inertia carry it forward in a straight line in a constant velocity. We have the force of tension acting towards the center. So again, in this case, the force of tension is the centripetal force. Here we have our car moving in the direction of the green, now red arrow. And so again, it could be constant velocity of whatever, 5-10 meters per second. So the centripetal force is the frictional force acting towards the center of curvature, causing the car to accelerate. And again, if you go around a bend too fast, actually, let's take a look at our equation here. V squared over R. So this force is the force needed to keep this set of parameters moving in a circular path. So if the velocity here goes up, what does that do to the centripetal force needed to keep that object moving in a circular path? Let's say velocity is doubled. What does that do to the net force needed? Okay, hopefully you said that it increases it by a factor of 4. So what that means is that if you're going around a curve in a vehicle and you're supposed to be going 15 miles an hour, that's the recommended speed, and you're instead going 30 miles an hour, then you need to be able to have 4 times as much friction between the wheels of your car and the road in order to maintain that turn radius. Whether or not that friction can be exerted is then, of course, dependent on the mass of your car, the normal force, and the coefficient of friction between the two surfaces. Asphalt and rubber have a fairly high coefficient of friction, which is why it's what's used for roads, and it's cheap. But as soon as you put a little bit of water on the road, as soon as you put a little bit of ice on the road, all of a sudden that coefficient of friction drops drastically, and now the maximum amount of force, frictional force that road can exert on your tires also drops drastically. And so if you exceed a required force greater than what the frictional force can be, that's when you end up in a ditch. So keep that in mind next time you go flying around a sharp turn. Also interesting to note, as the radius goes up, the centripetal force needed decreases, right? And if you think about traveling around in a tight curve versus a much larger curve, it is a much easier thing to go around the larger curve. It takes more time, but it requires less force at the same velocity.